Let's have a look at some Go programming with some cryptography. And the application we'll look at is within trusted voting. So we'll see how we can set up a trusted infrastructure so that we can preserve the privacy of the voter while increasing the trustworthiness. And the focus of it will be upon the methods that were applied in this paper here. Okay, so what we want within our voting system is that we want some privacy for the voters, and we also want privacy within the voting of the counting of the votes. So in a normal voting for an election, we might have Trent who will count the votes, but as soon as Trent sees the votes from each person, then that could breach that person's privacy. If possible, we want interim results to be available, so it's possible at certain points in an election for there to be interim results on the number of votes cast and so on. We want a way for undecided voters to remain undecided. So it's not automatic that they will vote even though they are registered to vote. We want to make sure that the process is free against voting under duress. And we want to make sure that the vote has been done correctly and there's integrity within it, so that all of the parties can actually check the results of the vote and they can all agree as to the trustworthiness of it. So the method I'll outline is that we have a list of those involved in the vote. So we have Alice, Bob, Carol, Eve and Dave. They will then register their identity using a secret key, an X value, and they register with G to the power of X. Next, they will commit their vote in some way, and after this, they can cast their vote with this value here, G to the power of XY, and then G to the power of V, where V is their vote. The hash value shows their commitment to their vote, and the actual vote is here. At the very end, we'll have a tally of all of the results. The paper itself defines a smart contract running on Ethereum to implement this. So here's the code, and I'll go through the code and then I'll show you the whole of the code actually working. So we're using discrete logarithms here, and with discrete logarithms we have something like G to the power of X mod of a prime number. X can be our secret, and G to the power of X mod P. It's not possible to determine the value of X even though we know the value of G, generator value, and P. So with this, that's our secret. So each voter will create their own secret, and they can keep that private. Then they register their key, their voting key, as G to the power of X mod P. G is a large number and P is typically 1024 bits, at least in size. So the basic little function that we have is that we'll convert the value that we have to a big integer and Go that we have we've created a big integer function here which takes the value and converts it into a big int format. Next we'll take G to the power of V mod P, and that will give us our key here. And the next part, what we do is that this is the way that we preserve the privacy. We multiply our values, so these values will be registered and everyone will be able to see all of the registration key values. Then each of those is taken by each voter and the constructor on yi value by multiplying all of the keys up to their value, but not including it. And then they divide by all the values after their key. So this is the multiplication up to their key value, and then we divide after that, all the keys after it. This makes sure that this is the result. And we'll see later on that that's important for keeping the privacy and also to be able to reveal the vote and to make it simple to find the tally of the vote. So this is the function here. Okay, so we start off with 1, of course, and we keep multiplying. So the multiplication here, each time round here, we take the value of y and we multiply it each time. Okay, so the value of y are these values here. So we go round and round and keep multiplying it until we get to our value or one before it, and then we go on to a divide. So the way that we divide in this type of maths is that we do an inverse mod and then we multiply it. So we'll find the value of our y and then we'll do inverse mod and then we'll multiply that value and it should all work out. So that takes us up to the end there and then we'll return that value back. We can do a mod p in the end because we're working with a finite field. Okay, so this is the function that we call here. Each time for each voter, they'll calculate their key for that. Okay, so now each value has this yi value that they're now going to use to make their voting. So that's that bit in there. Okay, so they'll make their vote next. So that vote is there. So it's y, the y values to the power of the x value. So here, this is equivalent to g OII to the power of xi, as John Napier derived, which is the same as this here. And then we'll take our vote value there and do the multiplication for that. And this is the function here for then doing the tally of the votes. Okay, so we'll pass in all of the registered votes and then what we'll do is we'll multiply them all together as we have here. Okay, so it takes all of the g to the power of y to the power of x values that have been sent back for the votes, and then each of them will have the votes added on to that too. Then in the end, this part here is equal to a 1. So all of this is a 1. So we end up with this here, which is when we multiply values together, such as g to the 1, g to the 2, v2, we end up to g to v1 plus v2, and so on, or the sum of all the votes. So this here, we can now look to brute force that. So the value that we have returned back here is this value. And we go through all the possible values of the summation of the votes until we find a value of g to the power of x, or g to the power of a value mod p. If they're the same, we've actually brute forced the log here. So if we just show you the code running. Okay, so here we are here. Alice, we can make it a binary vote, a 0 or 1, but let's say that they're voting for a certain value here, and we'll go ahead. This is the result that we get. So we're using 512-bit prime numbers. There's the vote registration for each voter, which is g to the power of x. I'm not showing the value of x for each voter, but that will be, I've just made it a random value up to 10 to the power of 12 for each of the voters. We work out their registration voting key. This is the voter values that they'll have, the g to the power of the vote. And this is this voter key that they need to use to be able to generate their vote. Okay, and then in the end, this is our brute force of it there. Okay, so we can easily change these values, and hopefully in the end we'll get what the sum total is without ever revealing what the actual vote was. So there's the vote here for each of the voters, and it's not possible to tell from that value what the citizen actually voted with. Okay, so that's the code that we're using there. And we can use bigger prime numbers. I've just used 512 here, but it's possible to use 768, 1024-bit prime numbers, and so on. The larger the prime number, the more secure our voting system will be. Okay, so that's shown an example of Go and some crypto and looking at trusted voting.